Hello, welcome back to our lectures. Emeka Udenza is speaking. Today we'll be looking at lipid catabolism. This will be basically the last module of this class. We'll be looking at both the lipid and the amino acid metabolism. So, today we'll be typically looking at the breaking down of lipids, particularly fatty acids. All right, let's take it off from there. As usual, I have something beautiful for you. I have a quote by one of the very popular TV personalities in the United States, and a woman billionaire. She says, there's no such thing as failure. Failure is just life trying to move us in another direction. This is something to ponder about. Let's kick it off immediately. Catabolism of lipid. The catabolism of lipids, particularly fatty acid, is given the name beta oxidation. Beta oxidation means the breakdown of fatty acid, particularly. Fatty acids, particularly, is what you break down in the beta oxidation. Of course, by now you should have known that lipids are an efficient way of storing chemical energy. The chemical energy that is locked up in lipids is much more greater than what you have in carbohydrate and protein. So oxidation and breakdown of fatty acids is a principal source of energy equivalents, energy molecules. What are those energy molecules? So the metabolic oxidation of lipid releases large quantities of energy through the production of acetyl-CoA. Remember, anytime acetyl-CoA is produced, don't forget this, acetyl-CoA goes into the citric acid cycle, it generates 10 ATP. That is a lot of ATP generated. NADH also generates, remember, 1 mole of NADH, when we did the electron transport chain, gives us about 2.5 moles of ATP. So the generation of one of these is 2.5. It make it to is 5. And depending on the length of the chain of the fatty acid, you now decide the number of NADH and FADH produced. Remember, FADH gives you 1.5 mole of ATP. So these are all energy equivalent when they are actually produced. Now, triglyceride, or what we call the TG, is the main storage form of chemical energy for most organisms. Now, the energy yield per gram, like I said this earlier, remember that? The energy yield per gram of fatty acid oxidized is greater than that of per gram of both carbohydrate and amino acid oxidized. So they are actually efficient source of energy or calorie, despite the fact that eating of lipids nutritionally has a lot of bad names. But they are not very bad after all. There are unsaturated fatty acids that are not bad. However, whether we like it or not, they remain an efficient store of chemical energy. Then, again, the body is replete, has a lot of the phosphoacid glycerols. Of course, the phosphoacid glycerol is a key component of the biological membrane. Remember, we said the phospholipid membrane is made up of a lot of these phospholipids that have a polar head and then hydrophilic, a polar head and a hydrophobic tail. And of course, in the formation of the micelle of the membrane, they are the ones that will protrude to make contact. The polar head protrude to make contact with the aqueous environment. All right. So of course, this is a typical fatty acid now. Remember, every fatty acid will have the carboxylic head. This is fatty acid now, and the tail. Now, the length of the chain is what decides the number of acetyl-CoA that will be generated. So if assume we want to break this thing into two carbons, let's see, 1, 2, you break it here, another 1, 2, you break it here, 1, 2, you break it here, 1, 2, 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 break it here. So what that tells you is that you are producing about 1, 2, 3, 4, 5, 6, 7, 8. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is 16 carbon. That is why you have, this is 16 length carbon. So this is palmitic acid. That is why you are generating about 8 2-carbon units. This is 8 2-carbon units. So you're going to get 8 acetyl-CoA from the breakdown of this. That is to tell you, and each acetyl-CoA worth 10 moles of ATP. That will tell you how many ATP you're going to be getting in this process. So this is actually palmitic acid. Palmitic acid, because it is C16. Yeah, that is a C16 amino acid molecule. All right, let's take it off from there. Enough of the introduction. So now, before we even begin to talk about breaking down of lipids, or oxidizing them in beta oxidation spiral. They need to be digested. And the commonest store of this fatty acid, we said, is the triglyceride and phosphoacylglycerol. The phosphoacylglycerols are phospholipids, where the triglyceride just have 3 fatty acids esterified to the glycerol. So what it simply means, you're going to be breaking it into a few fatty acids and a glycerol. The glycerol can enter glycolysis and be broken down, whereas the fatty acid enters the beta oxidation spiral. So both the phosphoacylglycerol and triacylglycerol have fatty acid as part of the covalently bonded molecule that are bonded through the ester or the phosphoester bond. Now, bond between these molecules are broken down by the enzyme lipases. Lipases are those enzymes, digestive enzymes, that break down lipids. And what they typically do is to break down the ester bond or the phosphoester bond. So the lipases will break just the normal ester bond, whereas the lipases will break normal ester bond, whereas the phospholipases will break the phosphoester bond. Let's look at what is happening here. This is an ester. This is your machete coming to break this at this point. This is another ester. A machete comes in again to break it at this point. Now, if you look at this now, this is phosphoacylglycerol. There is a phosphoester here and there's another phosphoester here. So a machete comes here to break it, to release this fatty acid, and also to break here to release the phosphate group. And remember, when all these things are all broken down, you're going to be left with what? The glycerol that forms the backbone of both the triglyceride and the phosphoacylglyceride. Now, so triglyceride and phosphoacylglyceride, when they're broken down in the digestive system, right, they now enter the intestinal mucosa, the mucosal cells, where when they're absorbed, and they are now re-synthesized in the mucosal cells. So the triglyceride and phosphoacylglyceride are synthesized in the cells of the intestinal mucosal cells into what they are. So they now get back to the triglyceride when they're now combined again with their what? With the glycerol. Now, for transport within the lymph or the blood, the insoluble lipids are very insoluble in the aqueous plasma environment, in the aqueous blood environment. So what do? They are complexed with the lipoproteins to form chylomicrons. Chylomicrons are the lowest density lipoproteins. Now these lipoproteins are further modified into other lipoprotein particles, and they are now carried to the cells that need them for metabolism. So look at what is happening here. This is a triglyceride. The arrow group here represent, okay, let me just make it protrude, represent the fatty acid esterified. So this ester bond will be broken down by lipases using water because it's a hydrolysis reaction to release glycerol, and then the free fatty acid will now be floating. If you have phosphoglycerol, just like the phosphatidylcholine, what is going to happen here? Again, this is an fatty acid as R. This is another fatty acid. They're going to be broken here and be released. The fatty acid will be released. And again, if it's going to be broken down completely, what it means is that this phosphoester bond will be broken down to release the choline, and another one will be broken here to release the phosphate group. However, in what we're trying to demonstrate here is that removing this one and this one releases the fatty acids here, and then what happens? The glycerol phosphocholine now remains together. So this from this point to this point still remains intact. That is our glycerol phosphocholine. However, our interest is what happens to this amino acid. That what happens now? It is either reused to form a triglyceride, or it goes into beta oxidation, and that is our interest. This is our interest, what happens to it. So the first reflection question says, where are phosphoglyceride resynthesized during digestion? They are resynthesized in the what? In the intestinal mucosa cells. This is where they are resynthesized. Do not forget that. All right, let's move on immediately. Now, what about the energy from fatty acid? I already told you, when they're broken down, they release a lot of these reducing equivalents, the FADH2 and NADH2, which work a lot in ATP equivalent, and also acetyl-CoA, which when it goes through the citric acid cycle releases huge amount of ATP as well. So carbohydrate from the dietary sources and glycogen catabolism are used preferentially for energy production. Yes, the body prefers to use the carbohydrate sources for energy. It doesn't just like using fat, except when there is need. So when the body's store of glycogen, in extreme fasting example, when the body's store of glycogen is highly depleted, the fatty acids are now called upon to be a source of energy. Now, what is the significance of this? The significance of this is that there are just backups for energy sources when the body does not have the immediate sources, as usual, which is carbohydrate. Now, the significance is that they help to conserve the glycogen store, because there should always be the glycogen stores, it doesn't run out completely, and the glucose for use by cells that cannot easily use other sources of energy. The brain is not interested in using other sources of energy. So the brain cells, which cannot directly obtain other nutrients from the blood, because of the blood-brain barrier, the blood-brain barrier will not be permeable to anything. It just only wants glucose. Therefore, those glucose molecules will have to be conserved for the brain cells. And not just that alone, the red blood cells or the erythrocytes, which do not have mitochondria, and therefore they cannot oxidize fatty acids. So what they rely on is what? Is also glucose themselves. So this is why this is very important, so that the glycogen store will be what? Conserved, and glucose will be there for the brain cells and the red blood cells. So let's talk about fatty acid mobilization. You see, when this, remember, the fatty acid is stored in the adipose tissue cells. The fatty cells are stored in the adipose tissue. So in the adipose tissue cells, what happens again? They reform as triglycerides, and they need to be broken down again. So that, what happens? So that the fatty acid can now get into beta oxidation. So when the body cells need fatty acid for energy, the endocrine system is actually what stimulates what? The production or the breaking down of fatty acid, of triglyceride in the adipose tissue. So the hydrolysis of stored triglycerides is followed by what? The entry of fatty acid and glycerol inside the what? Bloodstream. So when these fatty acids get into the, remember, when they get into the bloodstream, they get into these tissues, they are restored again. They reform as triglyceride and they're stored in the adipose tissue. Now, for them to be used, they have to be broken down again. And it is a hormonal signal, particularly by what? The enzyme epinephrine, that stimulates lipases and phospholipases, that goes there to do what? Like I said, the epinephrine stimulates the lipases so that they will hydrolyze or break down what? The triglyceride, and now releasing what? Fatty acid. That process is what we call the fatty acid mobilization from the adipose tissue. So in the blood, the mobilized fatty acids form a lipoprotein with the plasma protein, of course, called the serum albumin. Like I said again, in the blood plasma, the lipids cannot be transported because they are very hydrophobic. So they have to be complexed with either lipoproteins or other protein molecules. In this case, in the bloodstream, in the blood plasma, they are complexed with what? A serum albumin, which is a typical transporter for insoluble material like plasma in the blood. So the serum albumin then transports them to tissues that need them for energy. Of course, the glycerol itself is water soluble. It can easily be carried in the blood because it's highly, remember, glycerol has what? 3 hydroxy group and is highly soluble and can easily move around in the blood. And what happens to it? It quickly, glycerol itself quickly enters, undergoes some modifications, and gets into what? Gets into the tricarboxylic acid cycle. So, like I said, the glycerol is water soluble. It dissolves in bloodstream and is transported to the cells that need them. Alright, so in reflection too, it says, what is the role of epinephrine in the fat cells of adipose tissue during fat mobilization? The main role is to stimulate the hydrolysis of what? Of triglyceride in the adipose tissue. Or you can say the mobilization. That is exactly what we call the mobilization of fat. So the word mobilization is used to differentiate it from what happens in the digestive system by the digestive lipases. The digestive lipases are different from these lipases in this case. These lipases are stimulated by what? Epinephrine or adrenaline. If you don't want to call it epinephrine, you can call it adrenaline. So let us now talk about glycerol before we now move into what happens to the lipid itself. So glycerol, of course, it undergoes a little bit of modification. First, glycerol is converted to glycerol phosphate, glycerol 3-phosphate particularly. And what simply happens is that ATP transfers the phosphate group to this point. This is a phosphorylation reaction. And the enzyme that does this is glycerol. Okay, let me just write one. The enzyme that does this first is what is the glycerol kinase. The glycerol kinase. Oh, okay. Well, let me shift a little bit. Okay, this enzyme is called the glycerol kinase. A kinase enzyme is an enzyme that transfers the phosphate group from ATP. Now, in the second reaction, glycerol, it transfers this to form the glycerol phosphate. Then glycerol phosphate undergoes dehydrogenation, or you can say oxidation, because oxidation is the loss of hydrogen. Look at what is happening. It loses this hydrogen and forms a ketone here. That's exactly what happens here. So, and this hydrogen, it loses it to what? The energy. So this is a dehydrogenase enzyme, which is NAD dependent. So the enzyme that comes in here is what? Is, you call it the glycerol phosphate dehydrogenase. The glycerol phosphate dehydrogenase is what acts on glycerol phosphate and converts it to dihydroacetone phosphate. Remember, dihydroacetone phosphate is an intermediate of glycolysis. What happens? It enters the glycolysis and is broken down to pyruvate. That is exactly what happens. That is the fate of glycerol that is released after the mobilization of what? Fatty acid from the adipose tissue. All right, what happens? Then what happens to the fatty acid? The fatty acid itself now enters the beta oxidation pathway. Before it does that, something happens. It needs to be activated. Now, activation of fatty acid simply means using high energy to complex CoAH. Remember, CoAH simply means coenzyme A. The coenzyme A has the sulfhydryl group. So what it does is that this hydrogen goes off, and this sulfur group is now attached to this one to form the thioester bond. Remember, this is what we call the thioester bond. It is this thioester bond that forms a high energy bond that makes this molecule to be activated. The enzyme that does this activation, so this is our fatty acid now. The fatty acid is acted upon by what? SC-CoA, or you can say fatty SC-CoA synthetase. The fatty acid-CoA synthetase uses ATP, what actually uses 2 moles of ATP to do this process to produce, and it takes this to attach this point to form what? The fatty acyl-CoA. So this is fatty acyl-CoA. This is the activated fatty acid, which now gets into the beta oxidation. And that is what we're going to be talking about next. So remember, much more, another important point I need to make. Now, this activation takes place in the cytoplasm, but the rest of the beta oxidation is taking place in the mitochondria. So what happens? So after this activation, the fatty acid-CoA, or the fatty acid that is activated, now crosses the membranes of the what? Mitochondria, and gets inside the mitochondrial matrix where beta oxidation begins to take place. Now, before we look at that cycle particularly, I want to highlight something. You see, like I said, after activation, fatty acid-CoA molecule enters the mitochondria. It enters the mitochondria, and then it is now degraded in the beta oxidation spiral. Now, look at what is happening. In the old nomenclature, I want to show you now, in the new nomenclature, in IUPAC, you're going to count this as carbon number 1, 2, 3. In the old nomenclature, this is usually not number 1. It uses the Greek name. The carbon number 1 is usually, we see this as an attachment to the carbon number 1. So this is the alpha carbon, this is the beta carbon. Beta oxidation simply means is that in the final step, this bond will be broken at this point between alpha and beta carbon. So what actually happens is that in the second to the last step, this beta carbon will be converted to a ketone group. After conversion to this ketone group, it will now be broken. Look at what is happening. In the last step, which uses coenzyme A, what happens? See, again, look at the alpha and look at the beta. It has been converted. So it will now use coenzyme A, an enzyme which we call the thiolase that breaks it. Will now use the coenzyme A, attaches coenzyme A to this one and breaks up this one. So this one that is broken up is now the new acetyl-CoA. So the actual objective of beta oxidation is to always break, depending on the length of the chain of the fatty acid, into a 2-carbon unit of acetyl-CoA. Every fatty acid or every beta oxidation spiral will lead to a fatty acid that has been reduced by 2 carbons. It will be shorter by 2. Let us not talk too much. Let's go into what is happening. Like I said, I've explained the first process. In the first process, what happened is that it was activated. Like I said, fatty acid, remember this is the fatty acid, I will say Fa. The fatty acid was converted to fatty acetyl-CoA. This is the fatty acetyl-CoA. Now, the enzyme that does this, I told you, it is the fatty acetyl-CoA synthetase. Now, this is happening in the cytoplasm. Quickly, it crosses into, now, this is the membrane. This now is the membrane, the mitochondrial membrane. What happens? It quickly crosses into the membrane through some specific transporter that is not in the purview of this class. It has a special transporter that actually does that. It's not in the purview of this class. Now, it crosses this membrane. Remember, I told you this is the membrane here. Good. It crosses this mitochondrial membrane and then gets into the mitochondria. It's inside the mitochondria that the actual process takes place. Now, the beta oxidation spiral consists of just 4 reactions. Look at the first reaction. Reaction 1, reaction 2, reaction 1, reaction 2, reaction 3, and reaction 4. Reaction 1 is a dehydrogenation reaction. Remember, every dehydrogenation reaction simply means oxidation, because oxidation means removal of what? Oxygen. That's what happens. Let's see what happens here. Now remember, this is the alpha carbon, this is the beta carbon. In the first reaction, that alpha didn't show up well. Okay, that's good now. In the first reaction, look at what happened. An enzyme that is called the FAD-dependent fatty acetyl-CoA dehydrogenase. That's the enzyme that comes in here. We don't need the name of the enzymes in this class. I can always tell you the names, but we don't need the names in this class. Okay, I can just write it, but you're not going to be asked of any of those names in the exams. Be rest assured. Now, what happens here is that an enzyme, like I said, it's called a fatty acetyl-CoA dehydrogenase. Removes hydrogen. Look at what it does here. It comes here and removes hydrogen between alpha and beta carbon. The moment it removes hydrogen, it introduces a double bond to form this. So the fatty acetyl-CoA will now be converted to a new compound that we call the fatty enoyl-CoA. So this actually has enoyl, means it has what? It has a double bond. Remember, like as in alkenes, fatty enoyl-CoA. That's exactly what we have here. Because of this, so the double bond is now between the alpha and the beta. In the next reaction, a hydroxylation enzyme, an enzyme that introduces water molecules coming. And this enzyme is called what? It's called a hydratase. Enoyl-CoA hydratase. That's what it does. Hydration means addition of water molecules. So this enzyme is called fatty enoyl-CoA hydratase. This is a hydratase. So you just say fatty enoyl-CoA hydratase. Just remember, the way we name enzymes is that you put the name of the substrate or the product is going to act and not put what the enzyme does. So a hydratase enzyme adds what? Water molecule. Where does it add? Remember, water molecule constitutes of OH. Every water molecule, remember, H2O simply means H plus OH. Now listen what happens. The OH is added to the beta carbon. Look at it. The OH is added to the beta carbon. So this is again the alpha. This is what? The beta. The OH is added to the beta carbon. The hydrogen was added to this to saturate this bond again. And the new compound formed is the beta. Remember, this OH is in the beta carbon. So we call this the beta hydroxy fatty acetyl-CoA. That's exactly what we form. We now form a beta. Now we now form something that has a fatty acid, activated fatty acid that has OH group at the beta carbon. In the next step, what is happening? In the next step, again, a dehydrogenation reaction is occurring. Remember, dehydrogenation reaction is an oxidation reaction. So there is another oxidation reaction at this point. In oxidation reaction, let's see what is happening here now. This is very critical. Again, this molecule loses, remember, it has OH here. This OH here now is lost, and this H is lost. When you remove this, let me use a different color, let me use yellow. When you remove this, no, that not the OH, the H alone. Okay, let me just highlight it. I think highlighting my work. Yeah, let's do the highlight. You see this? Removing the H from this and removing another H here, you are removing two hydrogens. So the removal of those two hydrogens, one of them is taken. Remember, anytime you have NAD plus to be reduced, it accepts one hydrogen, one of the hydrogens is floating. So look, these are those two hydrogens that is lost from here. Losing this makes it to form what? It forms, remember when you remove one hydrogen and another hydrogen here, two hydrogens, it forms a ketone group at this beta carbon. Remember, this is still the beta carbon, and this is the alpha. So now this molecule form now has a new name because this beta, this carbonyl group or the keto group is on the beta carbon. We now call it we now call it beta. Okay, no, call it beta keto fatty acyl-CoA. Call it, that's the name. Call it beta keto acyl-CoA. Or you can say, yeah, beta keto acyl-CoA, because the carbonyl carbon is located in the beta carbon. Now, what happens in the next reaction, which is the final step? Remember, this is the step 4. Remember, this is step 1. This is step 2. We've done step 1. Oh no. Okay, let me use yellow. This is step 1. This is step 2. We just did this step 3, which is another dehydrogenation or oxidation. Now we are in step 4. What is happening in step 4? In step 4, look at what is happening. An enzyme which is called the thiolase. This is the thiolase enzyme. Remember here, the enzyme that does the job again is a dehydrogenase. This is a beta hydroxy fatty acid-CoA dehydrogenase. This is the enzyme acting here again is a dehydrogenase. So what happens? Now, in the last reaction, the enzyme beta keto fatty acid-CoA thiolase comes in to break the bond at this point. Look, let me use a different color. Comes here to rip this bond between, is a machete. Thiolase is a machete that comes to break the bond between the alpha and the beta carbon. So, wait, that thiolase doesn't seem to be very clear. I'm going to write it. Okay. This is thiolase. Yeah. Okay, good. Now, so the thiolase comes, but in doing this, it's doing two things. It is breaking the bond between the alpha and beta carbon to release, look at what it's releasing. It is releasing this thing as acetyl-CoA. And then it is also attaching another coenzyme A to the remaining carbon. So the remaining of this will now get another attachment to form another activated fatty acyl-CoA. And the process continues. This is what we call the beta oxidation or the fatty acid spiral. Now, let us take important notes. What has happened here so far? Let's see what has happened here. Let's take stock of what we see. In the first reaction, one FADH was produced. Let's write it. Oh, no, mistake. Let's start from activation. In the activation, what happened here? Two ATPs were used. So usually 2 ATPs were lost. You can say 2 negative. Now, that is in activation. In the spiral itself, in the beta spiral, what is happening? In the beta spiral itself, let's see what's happening. In the spiral itself, what is happening? In the first reaction, 1 FADH2 was produced. In the second reaction, no energy equivalence, we don't have any interest. There's no ATP or NADH or FAD. So in step 3, another oxidation. Remember this oxidation here. Oxidation produces, another oxidation reaction or dehydrogenation produces this guy. So we get 1 NADH. Nothing happens again. In this reaction, there was just formation of this carbonyl, this keto group on the beta carbon. We don't have interest. In the last reaction, the TLS comes to cleave off what? Acetyl-CoA. So what it means, in the fourth reaction, there is also 1 acetyl-CoA molecule that was released. So one complete spiral will produce one. Remember, the activation will only happen once. It's not part of the spiral. It happens only once. However, the beta oxidation spiral will do what? We'll use, in one cycle, you produce 1 FADH2, 1 NADH, and 1 acetyl-CoA. And the spiral will continue depending on the length of the fatty acid. Like the one I showed you earlier when we started. The palmitic acid has what? 16 carbons. If you have a 16 carbon fatty acid, what it means is that you're going to be producing about 16/2 8 acetyl-CoA by breaking it into 2. Just do 16/2, you're going to get 8 acetyl-CoA. Then how many FADH and NADH are you going to get? We're going to get back to this much later to know how we now determine the number of the reducing equivalents that is discovered. Just for now, the first thing you need to take away here is that in the spiral, to get the number of acetyl-CoA produced, divide the number of carbon of the fatty acid, the total number of carbon, by 2. That tells you the number of acetyl-CoA that will be produced. So if it is a palmitic acid that has 16 carbons, we're going to have 8 acetyl-CoA produced. And this is the beta oxidation spiral. We now go and take the next reflection question. It says, where does beta oxidation occur? Remember I said it. The beta oxidation occurs in the mitochondria. It occurs in the mitochondria, not in the cytoplasm. What happens in cytoplasm is activation, not in the endoplasmic, not in the Golgi body. It occurs in the mitochondria. The next reflection says, which is the last reflection and the last slide. It says, where does activation of fatty acid take place? Remember we said this. The activation takes place in the cytoplasm. So it is easy to get that. It does not take place in the endoplasmic reticulum. It does not take place in the Golgi body, and it does not take place in the mitochondria. What takes place in the mitochondria is the actual beta oxidation itself. And having said that, with this, our reflection 4, we've come to the end of this lecture. Thank you for listening. Bye.